Okay? Okay. So thank you for coming. It's our last presentation of today, and maybe like everybody tired, and so I appreciate you coming here and listening for this presentation. The presentation is pretty detailed. We tried to put in our slides as much as possible information, logically organized, not so many pictures. The reason is that we'd like you to use this presentation as a sort of an article, as your reference material, and in case you're interested in future, would like to ask some questions or look at again. During presentation, I possibly will skip some details just to be on time and giving you maybe some additional input on interesting topics. So why phase 2? Phase 1 is been 2 years ago, and we presented our research on malicious hypervisor threat. It was DeepSec 14. We put 3 years of our time after a job and sometimes additional time, because we considered and still consider malicious hypervisor as the highest level of threat whenever happened to information systems. Why so? Because malicious hypervisor is exploitation of virtualization technology. It's unlimited in power. Malicious capabilities depends only on hypervisor developer imagination. It could be from getting any bit of your data and up to complete destruction of your system. You're just taking your system and going to dumpster to throw it out. Sometimes, in my opinion, it cannot be fixed at all. That's the reason. And the phase 2 actually outlines our efforts to fix the situation, at least in detection of such malicious hypervisor, not to protection. Protection, I don't know, maybe somebody will develop it or us will work on that matter. But our target last 2 years was at least to detect, because previously we were saying like we don't know how to detect a hypervisor if it exists in the system. So the history. We have 2 big topics today. Phase 1, just to remind people who've been here, or to outline the most important things in presentation, as it was 2 years ago for people who didn't have a chance to see it. Phase 2. What we exactly done to detect the hypervisor, our research and development. So phase 1, refreshers. Phase 1 consisted of consideration of 3 cases. Case number 1, it was initial case which triggered our research, and we named it Russian case. It happened around 2011, 2012, that one Russian research, one Russian scientist posted on Russian hacker site, a blog site, a blog explaining his efforts and his dissatisfaction and what he actually found and what he did. It was around 2007 that he found a malicious hypervisor in Intel motherboards. He received from a source, possibly from Canada, and those motherboards he finally identified as having a malicious software in. this software interfered with his own hypervisor design. He tried to identify what was the source of such hypervisor on motherboards, and finally he found that it's been embedded in BMC flash memory. He also found that those the motherboards labeled as assembled China were having such malware, and labeled assembled Canada not having. Okay, so he tried to work with Russian authorities on that matter. Of course, understanding that such hypervisor is a huge threat, and but he was really dissatisfied because Russian authorities actually he was working on that matter he was giving two presentations to so-named FSB, it's former KGB. This organization currently is working on information and communication security. So he worked twice with them, and they dismissed his case, saying like, we are not interested, etc., etc. Of course, they were interested. Okay, of course, they got the message. However, he was disappointed and posted this blog explaining everything, including how he worked with virtualization technology, how he tried to identify the hypervisor when it became completely invisible. One note, it was like over time. He didn't put exact time, but what was interesting, he was watching on how malicious software interferes with his own, and found that it's improving from time to time. It's like it was continuously improving until he worked with his own hypervisor without any interference from malicious software. After we worked on that matter, we translated, and we were trying to figure out where such a hypervisor could come from. What could be the source, if it's publicly available. And very soon we've actually found Michigan University research which been published in 2006, and actually I think so it was done between maybe 2004 and 2006, or 2005, 2006, and this research was exactly as Russian case. Michigan University been tasked by three sponsors, Intel, Microsoft, and Department of Defense, to identify a virtualization technology or virtualization software which would be able to complete control of a computing system. So that was exact purpose, to find a software which would completely control computer system and could exploit whatever they actually want to exploit. The case number 2 was interesting, that people actually explained everything was done, put testing information on, explain exploiting capabilities. However, what was interesting that they didn't discuss how this hypervisor, their software been loaded on the system. This is like CD-ROM, for instance. That was really interesting because in Russian case, the scientists found the hypervisor already embedded in BMC flash memory. Okay. After case number 3, which left some questions, but we completely understood what could be a possible source of such a software. We found also yet another Michigan University research which actually added some value into malicious hypervisor. The research been done on IPMI, or it's Intelligent Platform Management Interface, and BMC controller, which actually is the implementation of this interface. So they found vulnerability of such solution and both IPMI and BMC. Vulnerability being so extensive that they been able by simple internet search to find around 100,000 services which could be exploited. So they proved the case. They explained how they found how such servers could be exploited, and in most cases, IPMI software or management software been actually simply not fixed for years. Okay, so it could be exploited in any manner you want to. So that is actually how our research has been done. The most important conclusions we've done in our research case number one were that embedding software in BMC bias required a lot of things. So it's not like you take it and do. You actually have to have Intel secret encryption key. You have to have BMC software code, software and hardware to work with BMC code, and flash memory, and actually to logistics, those boards being transferred. So it should come in your hands. You should change using what we already mentioned, and you have to ship it to the destination. So in our case number one, this Russian IT company. Other interesting thing was that it was our already own research that actually Intel Corporation never had assembling facility in China. Neither it had assembling facility in Canada. It was completely misleading, those labeling. Whoever did it, it was just like a stupid misleading. They could invent something better. What Intel has in Canada, actually in Vancouver, they have flash memory development facility. It's a flash memory group, its exact name. That's it. So I don't comment further on what Intel does, whatever facility does. So basically, that's what we found, some associations. Okay? Also, what was important is the time correlation between case number one and case number two. So case number one happened sometime around 2007, 2008, and case number two, it's around 2005, 2006. Also, the software which been developed at Michigan University didn't have hardware virtualization support. And as Russian scientist explained, he was actually using new Intel motherboards which hardware virtualization support, and the software which interfered actually didn't work with hardware virtualization support here. So this software was not able to address one additional virtualization level. So nested virtualization was not possible at all. Another question which we actually tried to answer during phase one and later, how many malicious hypervisor do we have? Perhaps have. Okay, we definitely know that there is code existing of Michigan University case number 2. We trust Russian source, and we believe that he had yet another malicious hypervisor case, and yet dealing with yet another malicious hypervisor code. So it's 2. And we do believe that after his talks with Russian authorities, guys took a note and wouldn't miss the case, wouldn't miss this kind of opportunity to develop their own malicious hypervisor. So we would believe that Russians also have malicious hypervisor, and possibly they used. Finally, what we tried to explain in our case, in our phase 1, that combination of 2 vulnerabilities. We name them vulnerabilities because we think so. One vulnerability each is virtualization vulnerability, and it's been implemented in case number 2 of Michigan University. And another vulnerability was implemented in case number 3, Michigan University. So coming together, there is highly efficient exploitation tool, and there is highly efficient delivery tool. So together, it's like almost like an ideal weapon. So in our research, we actually started with some sort of discussions with people we knew in information security industry, and we actually found that there is a sort of misunderstanding of us. We went through a few cycles of discussions, and finally figured out that a common understanding of vulnerability is around software bug. That's it. There is a bug, and there is a vulnerability which is caused this bug. However, in our case, we're actually dealing with completely different situation. This situation is, as we name it, technology vulnerability. It's much higher. For instance, what it means what it means for us, a vulnerability. Yeah? We are really vulnerable creatures. For instance, we cannot survive more than like 30 seconds or maybe 1 minute without an oxygen. We die. Okay? Our computers, after a certain time, they go down, and unless you provide the power, they don't work. That's also vulnerability. How we fix it? We provide power. We have batteries. We improve it. Yeah? However, that's vulnerability. In our case, we think that we deal with 3 vulnerabilities. First vulnerability is actually virtualization vulnerability. It means that using virtualization technology, we can install this malware between currently existing operating system and BIOS level. So we just put it in between. Okay. In this case, malicious software has complete control over operating system. Another vulnerability we deal with is IPMI vulnerability. It's a standard which has been developed by Intel. However, the vulnerability of the standard is that it permits complete and full control of computer system from its management interface or from its management software. Okay? So on, say, operating system level, on server operating system itself, to control operating system, we actually need root or administrator account. It can do a lot of things. However, when we talk about IPMI, it's absolute control. You can such software. Sorry. Such software can completely destroy operating system. It can actually control even a bias management software installation or update, etc. So you think you are updating management software, fixing vulnerabilities? No, it can trick you. It can just say to you, well, yeah, it's updated, like version next, blah blah. But in fact, it will be not fixed software. It will be still software with the malware, and thus you basically cannot fix such system at all. Who should take care? And yet another vulnerability is BMC as a unit, as a controller itself. Software which is installed there, it's server management software or computer management software. It actually has underlying operating system. In most cases, like I would say in all cases, it's Linux operating system like bare bone, which runs maybe HTTP server on top of, but it doesn't have any significant security controls which you can find in Linux system. For instance, personal firewall, SE Linux, automatic update and installation, etc. So there's nothing like that in BMC management server management system. It's just simple password control. That's it. Who is responsible for that? Well, in some Microsoft knew about Michigan University case number 2, of course, because they sponsored, and they knew about virtualization vulnerability, that Microsoft operating system could be altered, could be moved up and exploited. They definitely knew. Okay. However, we never found any word on that matter. Intel Corporation, as sponsor, also, of course, knew about vulnerability in IPMI, and also they knew about a vulnerability in BMC. However, we never seen anything from Intel Corporation on that matter. We tried before discussing that in public. We actually tried to address this question to Intel Corporation. We wrote an official letter, and we would like to discuss with them. Why? Because you see, Intel has 90% of CPU market. It makes chips for the motherboard. It makes motherboards, etc., etc. So you see the list. Yeah. So basically, it makes everything from hardware to software, which is vulnerable. We sent our letter to Intel Corporation, pointing that we we are trying to discuss with them cooperation on fixing technology vulnerabilities. So we explained that we are not talking about bugs. We are talking about technologies which are vulnerable, and we cannot definitely fix such technologies ourselves, and possibly even Intel Corporation cannot fix now, but maybe in future they can address these questions, and we would be in a better position. On the screen, that is the response. We exchanged a few emails with production security lead. We had one verbal discussion over the phone. I usually prefer being only on email because it's a protocol. Our discussion, of course, went to nowhere, and we didn't expect anything with such like Intel admitting that there are some vulnerabilities if we are going to work on that matter, etc. Of course not. They're not going to. Neither Microsoft would. You know, it's a corporate politics matter and all things around it. So they wrote formally that we didn't provide us with any new information concerning new vulnerabilities he found in our products, that you can address your questions to other manufacturers of server boards, etc., etc., etc. So basically, they sort of just dismiss the case. Okay, and I don't think so. In future, we will be able to work with big IT vendors on that matter. I think so. We are on our own. Just a few words summarizes that. So why IPMI and BMC are so vulnerable? First of all, of course, it was not security development like life cycle in such technology like IPMI. Even in new modification of IPMI, and that been addressed in discussion with Intel lead of production security, they are going to improve security in next release, which is maybe in a few years. The standard name is Redfish. They are going to improve something. However, we don't expect a real improvement of the approach. In the first way, any significant improve in IPMI, which provides seamless access to entire computer system from management interface. One note which Intel lead actually done, it was that they are, by default now, they are disabling network management interface by default. However, in our eyes, it's basically disabling IPMI and remote management features. You cannot really use remote management, remote server management, if you disable network. How are you going to do it? Going from server to server, working through a serial line interface on server farms, or sometimes your servers 100 miles away, or maybe 1,000 miles away. So how are you going to do it? So that's like typical answer and typical approach of vendors, and we actually need to deal with that. We shouldn't expect anything better, in near future, and we have to do something ourselves. So we are moving to phase 2, research and development. So existing ideas and what we have done the research of how to identify a hypervisor, install the computer system, and following development and testing of the software during last couple of years. Which method we used? Our goal was actually to simplify the software and simplify the approach, and do it really practical. Ideas and methods. What we needed to do was to identify 1% difference in time, in execution time. We decided to use this approach because other methods which we tried to identify whether we can use them, being actually not effective and actually suffering from a possibility that malicious hypervisor will actually disable or alter results of identification attempt. So we needed to do something different, and we opted for software which will do basic computer operations, which would not trigger malicious hypervisor to alter or to identify that there is identification attempt. Why we decided that we have to do like time identification of 1%? Because our idea was very simple on that matter. Any hypervisor consumes computer resources. First of all, CPU resource. If it's a good hypervisor, it shouldn't be like visible at all. So, for instance, currently we run around 10, maybe 20 virtual machines on one hypervisor. So, if one hypervisor consumes, like, say, 5%, then it's going to be completely useless and not effective. So it was more like common sense, expecting something around 1%. So next step was how to identify. Time identification method. We needed to find a difference in execution time between the same system with and without hypervisor using 2 phases testing. Why 2 phases? Because we need to compare. We need to compare what is execution time with hypervisor and what is the execution time of our software without hypervisor. How it could be done? First, trying to find a clean system right after the production. Another approach is statistically clean system. So we test several systems and find what is if results different, and which could indicate that some affected by malicious hypervisor, some not. So it's like collecting statistics. We expect like majority of systems are clean. Another way is simply disabling virtualization and doing the same kind of test. So, not all computer systems have bias virtualization control, and thus it could be done or not. not always. And also, we think that good malicious hypervisor, good designed hypervisor, could alter bias information. So you think you disabled virtualization, but in fact, malicious hypervisor didn't permit you to disable it, and you also only see like altering output. So phase 2 research, development, testing, statistics. So for our testing, we used simple computer system existing of 3 computers, 2 computers running virtualization software, and also desktop computer running VM client. We used VMware software as hypervisor, say malicious hypervisor, because we believe that VMware is the best available on the market, and I think so it is. The best available hypervisor on market, the most efficient, and it means if we can identify this hypervisor, other hypervisors could be identified as well. The most important is statistic filtering. From previous research papers we analyzed, we knew that statistics collected from hypervisors are really random, and deviation is really high. So our idea was to do a few steps in statistical filtering, and thus to move deviation to different level which would be acceptable. Execution of some operations. Finally, in our testing, we identified that increase in time difference. It's approximately twice. Increase in time deviation approximately from 2 to 50. Those results we actually achieved when we used pretty complex combination of operations, and some operations actually drive the hypervisor to the status when hypervisor actually starts the delaying and starting buffering some commands we ask to execute, and in this case execution time deviation increases really significantly. So this method we considered as really promising, because time deviation method is also acceptable, but it gives pretty insignificant value in deviation. That's about 0.7% or 0.7%. When we move to deviation difference identification, we have completely different pictures. So we have increase in time deviation approximately to 1.8%, and also the deviation increases from 2 to 50 times. In this table, we see the results of running hypervisor. So it's VMware running our software without hypervisor. Next, couple tables. We actually did like 40 tests, which gave us statistics to identify what happens with hypervisor. without hypervisor, if you see here, the deviation is really insignificant. It's 0.008. It's like 0.001. Okay, one tenth, one thousandth. Okay. When we move to running in hypervisor environment, we have, you see, like some results are in bold, and those results are really high, like 0.3, 0.1, 0.4. So, and average deviation for by 10 runs is really high. On this slide, I would skip the most of information, only providing you with the final result. Is it possible to identify the hypervisor by time difference method? Because the time difference is 0.0979 is more than 4 times the maximum sum of average standard deviation, which is 0.9, and it means we actually have statistically correct result. So the time difference which we identify is 4 times more than deviation. So it's statistically correct, and that is what we could do. How we can use time difference identification. However, by deviation increase, we can do significantly better. As you see on the slide, and it's actually lists, we have high deviation results in each of 4 tests by 10 runs. Okay, so it means that in the case of hypervisor, we have really high deviation. Okay, so instead of finding time difference, we can work with just deviation difference. Just a second. Okay, so we created some thresholds, and you can see here that is our say sample. So it's like theoretical picture, and which you see at the bottom. It's like how deviation changes, like in without hypervisor, and on the top you see stars showing how deviation would be different from without hypervisor. So with hypervisor, it's significantly higher. So those are results in real results which we have running our software, and it shows the hypervisor identification process. So instead of using numbers, which is really hard to use, and with numbers, a person who works with our identification software needs to figure out, is it high deviation or low deviation, etc., etc. Instead of that, we created a really simple GUI interface where you see yellow crosses, and out of 5, you see 4 which which are on the border or higher than hypervisor identified, and only 1 is hypervisor is likely. Okay. So next.
Sorry to interrupt you. You have 5 more minutes.
Yeah, that's it.
Okay, good.
Yeah. So next slide is actually very similar to the first one. Just provide some information on what. Okay. So we came into conclusion finally. We have now we have a software. We believe it's reliable and have good quality in identification. While we didn't test it on multiple hypervisors, we tested it on the most advanced on the market, and we believe the similar picture we will see in future. However, if anybody is going to join our research, then it's possible, and you can try other hypervisors as well. But we believe that now we have good identification software. There are two methods of detection, okay, and we used only one in our production software now, but both could be used. Time deviation also could be used. We don't expect any real help from major IT manufacturers like Intel, Microsoft, so we're basically on our own. I hope that somebody will join our research, would be interested in results, and then we can go ahead. So that's it. And thank you for your time and attention. So basically, I skipped a few things there, but if you have questions, I can address. I hope this presentation will be available on a DeepSec site very soon. You can look through it. We also have a text, which is like an article, and we'll improve it, and we'll send it to DeepSec as well, and hopefully they will publish. My email is here, so if you want to discuss something, feel free. All your questions over email will be answered. If you need, we will use encryption, and our messages will be encrypted if we really go into specific matters. Okay, but in general, our website, our email server is secured, which is robust.com, and we can exchange freely.
So thank you very much. We actually have two questions from the audience already, so we will do that rather quickly and then move on.
My question is, there are special instructions that you need for implementing an hypervisor, and these instructions, when already being trapped by another hypervisor below you, should have different timing. So isn't it possible to simply concentrate on the virtualization instructions for identifying the hypervisor via timing?
Okay, I'll try to answer. Yes, I understand. Okay, basically, there are two. The most standard method is identification of hypervisor activity from operating system environment. So basically, hypervisor is below, operating system is above, and you're running software inside operating system, and you're trying to identify specific signatures associated with commands which a hypervisor performs. So in this case, a hypervisor can trace your activity. That's one. Secondary, this situation is statistically unstable, so it's hard, really hard to collect statistically stable information. In our case, I skipped it, yeah? So I'll add, instead of running within operating system, user operating system, we shut down user environment. Additionally, it makes this identification secure because you don't interfere with your environment. We load our operating system and we load our software and start it. If there is a hypervisor, it will be always there. A good hypervisor will sustain reboot and shutdown process even on on management part. Okay, so basically we do not trace hypervisor activity. We just execute our software and measure inside our operating system environment, and we measure this time. We don't touch hypervisor at all. It's only it only makes the process happening, because it translates all information through the virtualization environment. Okay, it emulates, but we don't touch hypervisor.
My question referred to not doing it from inside the operating system, because I agreed to you that this is hard, but instead of the operating system.
Just
so you have something started from, say, some memory stick or something.
Coming down, just a sec. Hi, it's gonna be easy, okay? Hi, go ahead.
My question was not from detecting it not from inside the operating system, but detecting it from something that runs instead of the operating system. You run something that can do hypervisor relevant instructions before starting an operating system, just a special software just for detecting if there is a hypervisor on the system already or not. And this software uses hypervisor instructions and
Our
tests
software?
how long these hypervisor instructions, hypervisor relevant instructions, which the hypervisor must catch, which is below you, to trap your attempts at getting at the hardware. So you can at least identify if there is a hypervisor below you by just calling these hypervisor relevant instructions, because they will have to be longer in execution than without a hypervisor below you.
Okay, so basically I'm talking that, for instance, in one research it was named like secure hypervisor, yeah, above, and malicious hypervisor below.
Yeah.
And from like good hypervisor, you're catching instructions which actually executed.
Yes.
Basically, okay.
You have to do the same.
Could we have a short public answer, and could you take it to the
We will
one-on-one?
discuss it.
Let me discuss it.
Yeah, we will discuss
Okay,
it. Yeah.
because I have one more question, then we will close this off.
It's more like a comment. I've had a similar talk in the 2013 Caro workshop in Bratislava from Richard Ford, who also presented similar detection mechanisms against hypervisors. So I would recommend you look up, because there's prior research on this topic.
When? Who presented?
Richard Ford, Caro workshop, Bratislava, 2013.
Maybe we'll give exchange a link or give him a link
Okay.
or something afterwards.
check.
Okay. So and
Nothing is perfect.
once again, Michael, thank you very much for your
Thank
talk.
you.
Thanks a lot.
Thank you for your time.